Just look at this image. I mean, it's absolutely stunning, right? You can almost feel the sun, smell the pine trees. Our brains instantly see this incredible landscape. But to the computer that's showing you this picture, it's not a landscape at all. So what on earth is it actually seeing? So here's what we're going to do. We're going to peel back the layers of this beautiful image and see it just like a machine does. We're going to break it all the way down to its most basic parts and then build it right back up again. Let's get into it. If we zoomed in on this photo, like way, way in, that majestic mountain would just disappear. The whole scene would vanish. And instead, you'd find this simple grid, kind of like a sheet of graph paper, made up of millions and millions of tiny single-colored squares. These are pixels. They're the absolute fundamental building blocks of every single image you see on a screen. Okay, now let's push in even further. So we're looking at just one of those little dots. See? It's just a solid block of color. It's one specific shade of blue for that piece of the sky, or one specific shade of green for that bit of a tree. There's no more detail inside the pixel itself. It's the smallest piece of the puzzle. And this is the crucial leap. A computer has no idea what sky blue or forest green means. It doesn't see colors, it only understands logic. It only understands numbers. So every single one of those millions of colors in our photo, it gets assigned a specific number. The whole visual masterpiece just gets translated into a gigantic list of numbers. But what kind of numbers are we talking about? See, we humans are used to our base 10 system, with digits 0 through 9. Computers, though, they use a language that is way, way simpler. To really get what a computer sees, we've got to learn to speak its native language, binary. Binary is a base 2 system. And everything, I mean absolutely everything a computer does, from running a complex program to showing you this photo, it all boils down to a sequence of just two little symbols, 0 and 1, on and off, true and false. That's it. It's the most basic, direct way to represent information with electricity. So how in the world can you represent any number you can think of with just zeros and ones? Well, it's all about something called column weighting. It's just like our decimal system has a ones column, a tens column, a hundreds column, and so on. Binary has columns too, but they're based on powers of 2. So you have a ones column, a twos column, a fours column, an eights column. Get it? So to make the number 9, you just put a 1 in the eights column and a 1 in the ones column. 8 plus 1 is 9. Simple as that. And what if you want to go the other way? How do you turn a number like 150 into binary? It sounds complicated, but the process is actually super simple. You just keep dividing the number by 2 over and over again, and you write down the remainder each time, which of course is always going to be either a 0 or a 1. Then you just read that list of remainders backwards, and boom, you've got your binary number. It's a totally mechanical way to translate between our world and the computer's. Okay, now you can probably imagine trying to read a long string of ones and zeros that represents a specific color. It would be a total nightmare for a human. It would just look like a giant wall of digits. And that is exactly why programmers came up with a much friendlier shorthand. Meet hexadecimal, or hex as everyone calls it. It's a base 16 system. So to get 16 different symbols, it uses our normal digits 0 through 9, and then it just borrows the letters A through F for the numbers 10 through 15. The entire reason it exists is to make those crazy long binary strings way easier for people to read and work with. And here's why hex is so incredibly cool and useful. A single hex digit can represent a whole group of 4 binary digits. So instead of a programmer having to type out 1111, they can just write F. Instead of 1010, they can just write A. It cleans up all that binary chaos into something much shorter and way more manageable. So here's the main takeaway. Hexadecimal isn't really for the computer. The computer is still chugging along thinking in pure binary, in ones and zeros. Hex is just a convenient translation layer for the humans, the programmers and engineers who need to make sense of all that data. It's like a bridge between how we think and the machine's native tongue. All right, so we've got a handle on how computers deal with whole numbers, integers. And that's great for a lot of things. But what about all the other numbers? What about numbers with decimal points, or the absolutely gigantic and impossibly tiny numbers you need for stuff like 3D graphics or scientific research? Well, for that, computers have a different trick up their sleeve. So, computers basically have 2 main ways of storing numbers. You've got your integers, which are just stored directly in binary like we've been talking about. But for everything else, they use a format called floating point. The easiest way to think about it is like scientific notation. You have one part of the number that holds the actual digits and another part that tells you where the decimal point is supposed to go. It lets the decimal point, well, float around. And the range you get with floating point numbers is just mind-boggling. A standard 32-bit floating point number can represent values as small as 10 to the power of -44, all the way up to 10 to the power of 38. That is a 1 followed by 38 zeros. It's this insane level of precision that lets a computer calculate the perfect arc of a grenade in a video game or simulate incredibly complex weather patterns. It's the math that powers our digital worlds. Okay, so we've torn the image apart. We've broken it down to pixels, then numbers, then all the way down to the raw binary code. Now for the really cool part. Let's put it all back together and see how that code becomes real. It all begins deep inside the computer's memory as this massive, seemingly random stream of ones and zeros. That's it. That's the raw image file. Our beautiful landscape completely distilled into its purest, most basic digital form. Then, the computer's processor starts reading through that stream at an incredible speed. It grabs the ones and zeros in chunks, uses hex as a quick way to interpret them, and figures out the exact numerical recipe, the amount of red, green, and blue for one single pixel. And this process happens at lightning speed for every single dot in the entire picture. One by one, millions of these pixels, each defined by a number, are pulled from memory and placed in their exact spot on the screen's grid. 1920 pixels across, 1080 pixels down. And then the magic happens. When all of those millions of individual numbered dots are slapped onto the screen in the right order, our brain doesn't see the numbers or the grid anymore. It just blends it all together, and we see the final, complete, and stunningly realistic image we started with. It's a beautiful illusion, crafted from nothing but pure mathematics. So think about this for a second. If every breathtaking photo, every immersive video game, every song you listen to is really just an incredibly clever arrangement of ones and zeros, it makes you wonder, right? If something can be described with numbers, can it be created from numbers? Where's the limit? What can't we simulate?